Hello, everyone. I will go ahead and begin the webinar now. I'm Justin Paschall from the European Bioinformatics Institute, located in Kingston in the UK. And I will tell you today about the ELIXIR Pilot Action, which we participated in, on the interoperable controlled access for big data transfer technology for ELIXIR projects. One moment. Next slide. Okay, so this was a pilot that ran between January and November of 2014. And the goal of this pilot was to evaluate and develop technologies for secure and reliable data transport in ELIXIR projects, specifically motivated by the use case of data transfer within the EGA project between the EBI and the CRG, where we had more than a petabyte of data to transfer, and we have a regular program of transporting around 100 terabytes a month. We really needed scalable and reliable technologies, but we recognized that at the same time, this was a generic use case that is going to apply to ELIXIR as a whole, and thus we enacted this pilot action to evaluate the best strategy going forward for those projects. And the key participants in the project came both from the EBI and from the EGA node at the CRG in Barcelona, Spain, primarily Ilka, Alexander, Angel, Mark, and Jordi mentioned in the slide here. So there were some specific requirements for this project, which I want to lay the groundwork for. Specifically, the EGA is a large genomic and phenotypic archive for essentially millions of samples, all of which have many gigabytes of data of next generation and array-based sequencing. And as being human data, there are some specific requirements regarding security of this data that must be met. The data as it sits in the archive needs to be encrypted. The data that as it lands on the user's hard drive also needs to land in an encrypted format so it can be moved into the secure area where the data will be analyzed. And this differs somewhat from traditional systems where you may have the data in an unencrypted form on disk, and maybe you encrypt it during transit. We have requirements both data at rest and data in motion in terms of security. We needed a portable modular system. We had just gone through the process of expanding the EGA from being located only at the EBI to being a federated system, which includes the Barcelona, Spain installation at the CRG. And so we needed to break away from a set of technologies which was highly embedded in our local system and make sure that it's something that could be deployed in other places. And I'll talk about the architecture which made that possible shortly. It needed to be scalable and horizontally scalable in the sense that we need to make full use of whatever bandwidth is available and not be constrained with CPU processing, say, for encryption on either end. So we need to be able to add machines and to use all available bandwidth. And I already mentioned the requirement for dealing with encryption in a specific way. Some nice-to-haves, which we thought about at the outset, would be making sure that there's a simple management API, both a GUI and a programmatic API that can manage these data transfers, and also issues like automated retry of failed data transfers. As we found as we went through the project, those really aren't just nice-to-haves; those are requirements because without them, the amount of human time you invest in making this kind of system work can be just too much, even if your technology is 99.99% reliable. So I already mentioned some of the background. The EGA is a distributed project with archives both in Barcelona and in the UK, which serve as a depository and permanent archive of genomic and phenotypic data, which is then accessed in a secure manner by users who apply for and get access to data, and they can perform data downloads. It's not just an FTP site that anybody can go to and download. It has to have this layer of authentication, authorization, and security managing the data transfers. When the CRG joined the EGA project 2 years ago was to bring both archives up to speed, because one of the goals was to mirror data to increase availability and security of the data by having it in more than one place. And so we had this large backlog, which was at the time about 1 petabyte, that needed to safely and securely move between two locations. And then there was an incremental need to keep the data in sync on a weekly and monthly basis after that. And finally, we wanted our solution to be a generic one, so that we don't need separate systems to mirror between the CRG and the EBI, and to get also the data to our users or to additional nodes in the system in the future. We wanted a generic technology that can have one installation, one framework that can handle all of these use cases. So we looked at a number of technologies, some of which we had used in the past and some of which we were considering to meet this need. The first is simple FTP, which works, but it didn't have as much ability to manage transactions and to do error recovery as we would have liked. Also, the efficiency of FTP, depending on the quality of connection, varied a great deal. FTP can be quite fast to locations which are well connected to internet main lines, but if we're transferring data, say, to Australia or transatlantically, we found that the throughput of FTP really suffered. There's a commercial technology that we have used heavily called Spera, which definitely serves the use case of moving a lot of data. However, it doesn't provide the level of customization that we wanted in terms of integration with our system. Is really a two-stage process. First, stage all of the data into a location for Spera, and then tell Spera to do its job, and then clean up that staging area. And this produces a substantial hardware and management cost to use that kind of non-integrated system. Although it was high performance once it was ready. As I'll talk about in a second, the burden of staging the data is substantial, because the data in the EGA archives sit on disk in an encrypted way, and then when copies of that data are delivered to users, it needs to be re-encrypted with a specific password that is unique to that user. And to make individual copies for each user of these data was prohibitive, because you'd have a 10 gigabyte data set times 200 users, and we have 500 such data sets. And even if we were only distributing a fraction of the archive at a given time, you would need a petabyte more of just staging space to have to stage all the data if you couldn't do it on the fly. And so that need for on-the-fly custom encryption and streaming of the data led to the development of the custom Java FTP UDT client, which I'll talk about substantially here. And finally, I'll talk about a solution that we're very excited about in the future, which is a hybrid that uses many of the components of our custom system, but also brings in a commercially supported managed Grid FTP system called Globus, which has many attractive properties for managing these systems sustainably over time with a relatively small staff. So here's just a picture of our data transfer. And this shows that indeed we were able to move close to half a petabyte of data in really a single month of July. The blue bars indicate data that was moved between the EGA and the CRG in that month, and the green bars represent new submissions that came into EGA over that same period. So the good news here is that we are able to transport more data in a given month than we received new data that was coming in, which means we can catch up to ourselves and then eventually have everything synced and updated on a monthly basis. So that's good news. Really, this graph here is really a measurement of how well EBI and CRG are connected to the internet. There are pretty big pipes between the two. And in fact, a combination of technologies were used over the production cycle that's represented in this graph. Largely, it was Aspera that showed what happened in this graph. But in fact, the management cost to do that was substantial in terms of us manually staging and moving data, and we were happy to find that we could achieve the same levels of throughput with our custom technologies. So to give you some more details on the EGA use case, on the left is the EBI archive. It's an object store database called CleverSafe, and the data there sits encrypted on disk, such that even though it's within the secure EBI network itself, we wanted the data itself to be encrypted just in case anybody's poking around in that network. And there's a additional secure area which is within this question mark, which we'll expand in a second, which actually contains the keys which are used to decrypt that data. So there's several levels of security. And so then we have the user on the right. So we need a way to get the data from the secure archive, decrypt it, and get it to the user over the internet. So to fill the question mark in a bit more, there's this super secure area I mentioned called the EGA Secure Vault, which runs a service in it called the re-encryption service, which, based on requests from the user on the outside, goes and opens a pipe to the secure archive, streams data as encrypted bytes from the archive, uses the encryption key which is available in the vault to decrypt it, and re-encrypts the data with a user-specific key, which is then fed to the user. So this system has gone through several stages of evolution over time, and what we have we think successfully found in the last iteration, as we work to port this service to be a distributed one that also operates at the CRG in Spain, it's much easier to have a variety of small worker processes, these mini services in a service-oriented architecture, to break the problem into pieces and to provide a modular solution. So some of the mini services behind this larger activity are specific services which receive a request from a user to authenticate who that is, be it another group like within the EGA, such as the CRG group, or external users. There's a service which recognizes what specific data sets a given user is authorized to use and reports that back to the system. There are internal services which maintain the list of available files and where to find them in our system. This was a quite handy abstraction because over the course of the last 3 years, we moved from one back-end file system to the object store, which is now in place. And because of this abstracted service, the rest of the service, there was no dependencies, and we were able to very easily do a drop-in replacement of one file store backend for another, because the access to the file system was through this mini service. Similarly, there are specific worker nodes which do jobs like encryption, which again is nice for horizontal scalability, because if you have a CPU-bound process that you need to add more servers to because you're unable to saturate your bandwidth with just one, you can add another one of these services and do a load balancing to speed up any one of these components, actually, if it becomes a bottleneck. And they can all sit behind the sort of standard HTTP load balancing mechanisms to appear as just one service, even if there's more than one machine behind them. And again, all these services themselves are actually HTTP REST services, so they're all using a standard protocol to talk to one another. There's a service that specifically does the data transfer itself, and then one that monitors when a data transfer is successful or if it's not, and helps to manage the transfer. Again, on the subject of flexibility for deployment in different locations, this type of a modular system is nice because when the CRG goes to deploy this on their side, if they have a different backend system or a different way to track requests for data on their end, then they simply re-implement the specific module that they want to make different. They conform to the same API, and so they're able to sort of mix and match this set of reusable modules. Here's just another diagram of how many of these different services talk to each other down to the level of what ports listen to a given service and such. So this looks like quite a, and that is a concern. The more components you have, the more lines you have to draw on a diagram to show how it works. But luckily, there are ways then to package from the user point of view some specific points of interaction, which they don't need to understand the entire system in order to use it. So there's a number of different layers to that, as are represented in this diagram. On the farthest to the back, the biggest box on the right, called the demo client, is a command line Java application itself, which has, as I'll show in a moment, both an interactive shell prompt where you can give it various commands. You can also so it's an EGA-specific shell, if you're familiar with, say the Python shell or something. And also you can use it in a non-interactive mode. You can just set the parameters on the command line that you want to download this file, you want a list of the files available to you. You can run those as commands to the command line. But really, this client is just one of many potential clients. This is sort of the common denominator. We wanted to give somebody a non-programmer an application they can use if they want to. But I think the real flexibility and power of the system is that it's the components used to build this example. We call it the EGA demo client. That all of the components are actually still exposed for users who may want to build their own client or may want to integrate into their own application. There are both Java libraries that they can use directly if they want to compile into their Java project. And there's also then on the far left a REST API itself, which does the basic function. So this is not the REST API that communicates between the components, but this is an outward-facing API that has endpoints to do the basic things like list those files available to me, request a file to download, stop, and all the controls you would need can all be activated by just forming a URL like you would find in a browser. And then any programming language that can form easily such URLs, which is all of them, Python or Java and Perl, you can interact programmatically by using those REST API points. Okay. Okay, so just briefly some statistics about the data transfer that was able to be achieved. In fact, we are way overcapacity at the moment. We were happy to find that we could transfer 26 terabytes a day if we wanted to, and in fact that was quite useful for the bringing the 1 petabyte up to speed in terms of sync. In reality, right now we transfer between 80 and 100 terabytes a month of new data that comes in would need to be mirrored to the CRG, and then we have about 100 terabytes total a month outgoing to users of the EGA who need to download data, and similarly about 100 terabytes come in as new submissions each month. And this graph here is just a breakdown of our users of this the system in different countries. So I wanted to describe a bit about problems we faced and lessons learned, because there was a lot of work done by the team to make this happen, and not necessarily in the place that would have expected. It's almost always the case that 99% of these file transfers work fine, and then there are just some that don't make it, have to be retried, and just tiny hiccups from the system. So I think as with any production system, you spend 99% of your time dealing with the 1% of problem cases. I mean, and some of these were due to weird file names with unexpected spaces or underscores, or weird paths that mess up the regular expressions that we're trying to parse and use this data. We found one particularly pernicious problem where large files, 20 gigabytes, 50 gigabyte files, were just consistently failing, and it didn't matter if they had plenty of time, you could have transferred 10 times that amount of space. In smaller files, the bigger files failed, and this was clearly because a bigger file is just a bigger target for random failure, packet loss, and so the very big files we just couldn't get through sometimes, even after 5 or 10 retries. And this was eventually found to be a very sort of physical, technical problem with a router in one of our data centers. Had some weird power supply blip kind of situation where it was losing some packets, and we eventually this faulty hardware was replaced and really solved the problem. But it was difficult because the networks themselves fluctuate a lot in their throughput over time, and there are lots of random problems. So trying to find a consistent problem in a system which already is fairly noisy is quite difficult, and we could only find when we finally introduced a great deal of tracking and metrics to try to figure out what was going on. So sort of logistical tracking is very important to make these things happen. And so to talk a bit about the details of the encryption we used, there's 2 types of encryption we applied, and for somewhat different purposes. The GPG encryption, you're probably familiar with the public-private pair kind of keys which you use if you SSH into a Unix machine. This is good for data transfer when you don't have a point to do a handshake, because the archive itself can produce a public-private key pair, make the public key available to anybody. The users that want to upload data can encrypt their data with the public side of the key and send that to us. And this is a way to avoid having to have some other physical exchange of a key. So that works well, but the problem with GPG encryption is that the file itself needs to be downloaded in its entirety for any part of the file to be useful. And another method is to use something called the AES encryption, which is symmetric, so that there's only one key in that situation. So you need to have a secure pipeline established. But once you do that, you have a lot more options with AES, because the way that the bytes are organized, you're able to seek to a given position in a file just as if it had not been encrypted. And for genomic data, that's particularly useful because there are many genomic data files, BCF and BAM files, CRAM files, which are sorted by genomic position. And if you have a specific biological question that you only need data from a specific gene, then you can use this type of index to download only the slice of data that you want. So that's a very strong advantage for genomic data, particularly if there's a specific question being asked that involves a specific slice of the data. And so we are working towards re-encrypting our archives using AES and using that as a primary way to distribute data for this property of slicing and dicing the data. Another big issue, which is the impetus for a lot of technology development, is this requirement that we be able to stream the data from an encrypted source. Many options are available, as we said, including Aspera, if you have a physical file on disk that you can send in one big chunk. And those systems are also very good at because the entire file is already there, they can start in several places in the file and open up a number of simultaneous threads to download a very large file in a faster space, faster time. But as I said earlier, the trouble is that you need to materialize one of these entire files before you can start that process, and this is very difficult for us. Given the number of users and the size of these files. So one solution to that is at least to be able to break the data set down into working with one file at a time. So I can essentially have a revolving door where I take one file. A user may be downloading 100 files. But if I have a very streamlined system where I take each file out, it goes to the revolving door, it gets encrypted, it gets sent. Once they've confirmed to receive it, you delete the file from the revolving door area, and then you shuttle the next one through. Then with a relatively modest staging area space, you can gain the benefits of having whole files to be downloaded at once, but you don't have to prepare an entire data set the user to download, and you have such a large swing scratch space in maintaining this kind of a service. The difficulty with this is that you need an automated system to shuttle these files through to the revolving door, because you can't put it onto the FTP, then have the user go and grab the file, and then for them to email again and say, I'm done with this file, and then now you need to shuttle the next one through. This would just not be scalable to tens or hundreds of files. So you need a overarching coordination system that can manage the movement and confirmation that these files have been sent and received if you want to operate that kind of an automatic revolving door like what we would like. And the best solution we see to this is something called Globus Grid FTP, which is one of the services that we prototyped in this project. Here's a diagram of how that system works in prototyping. How we imagine it working in the future is basically a hybrid approach from what we had so far. So we keep the service-oriented architecture, which does the management of requests and tracking of who has access to what file and this kind of thing that we have already built. But instead of using the streaming custom system which we developed so far, we think that the Globus Grid FTP file transfer, which provides an additional level of API management on top of the file transfer itself, allows us to build a system which can automate all the steps of transferring a file, confirming that it's done, triggering an action once the file transfer has been complete, and essentially making the hands-off process from the sender and the receiver's point of view. So the way that Grid FTP works is you register a directory at both points, and essentially there's, in some sense, a server running on both ends which is able to talk to one another and watch the process of a file, a large set of file transfers, and make sure they succeed. So you can turn this on, and it can run independently for a week or 2 weeks. And it will check that all files made it and restart when you need to. It will take specific actions when a given file is complete. So like I said, you don't have to stage all 100 or 1,000 files at one point. To start this, you can have a trigger which verifies that a file transfer succeeded, and then it moves the next file in. So we see this as the best way going forward. Again, the final lessons learned, that automation is critical. The technology worked pretty well, and there more than one technology was capable of using our full bandwidth and moving a petabyte of data in a month. But the amount of time spent to debug and restart was prohibitive, and this is why again we're looking towards further ways to have an automation level on top of what we had before. Because in the end, your human time is the most valuable and costly, and nobody wants to spend their career pushing around failed files. You need a way to automate that process. And so finally, I'd just like to thank ELIXIR for enabling this pilot to go forward. The EMBLE BI and CRG teams had a great fun working together to try these different options and find what looks like the most efficient way going forward. You can find our 2015 Nature Genetics paper, which was recently out for the EGA, where it lists the full set of funding sources for the EGA. And again, listing here the primary participants in the project. Thank you, and I'd be happy to answer questions.